Hi students. So in this video we're going to be calculating the cell potential of particularly something called an electrolytic cell. We're going to go through some steps here, and the first steps are actually, the first step particularly is quite similar to the one that we had for balancing redox reactions. But what is the cell potential? I want to show you a list of these cell potentials so that you can see this. This is the list of the standard cell potentials, the reduction potentials particularly. I want you to notice that all of these reactions are reductions, right? In other words, when you look at the equation here, the half reaction, you have the electrons on the left-hand side indicating that it's a reduction. What you notice is that fluorine is all the way up at the top, and to reduce fluorine, it has 2.87 volts as its reduction potential. What that means is that fluorine really wants to be reduced, and so it has a really high potential for happening. That's the way you can sort of talk about it. It has a high potential. And as you go further down, these reactions are less likely to happen. Still, the ones at the top are very, have a high potential. So the reactions that are below the hydrogen, where you have hydrogen becoming hydrogen gas, are going to be negative. And what that tells you is that these are reactions that are not going to happen unless this reaction is given some sort of voltage and it's told to you what the particular voltage is. So for example, in order to reduce lead from lead 2 plus to lead neutral solid, you have to add at least 0.13 volts. That's what the negative sign implies. We have a name for this. This means that it is not spontaneous. So it's important. If you have a positive cell potential, it's considered to be a spontaneous reaction. This is important. I'm going to bold this here. And conversely, if it's a negative, then it's going to be non-spontaneous, in which case you need to add that voltage that is there. But those are just half reactions, reduction half reactions. We could actually figure out this whole redox reaction. And so what we have to do is write out first the half reactions. So that's what we're going to do. So this is the same problem as the previous video where we talked about balancing redox. This is helpful because we can add to this layer to the same problem. And so again, we have lead here. It's going from neutral to +2, so it's losing electrons, being oxidized. And then chromium is being reduced. And so we're going to write these half reactions. Lead half reaction is Pb and is losing, so it's going to be Pb2 plus 2e. And then this is the oxidizing half reaction. And the reduction half reaction is going to be Cr3 plus 1e yields Cr2 plus. Now, we already know that in this case, we're going to have to multiply this reaction by 2. But there's a note up here. You do not change anything having to do with the reduction potential. So let's go here and just take a look. So it's easier to start with the reduction because the chart that we have here is already in reduction, right? It's a reduction potential list. Okay, so we're going to start with a CR actually. CR3 plus 1E yields CR2 plus. Let's see if we can find that here. Looking. Ah, there it is. You see that CR3 plus 1E yields CR2 plus. And the reduction potential is negative 0.41. We'll write that over here, negative 0.41. Okay. Now, the next one, this is the oxidation one. So when we're looking for this, let's try to find it. The issue though, issue is that you're not going to see it as a reduction, or sorry, as an oxidation, you're going to see it as a reduction. So we're going to try to find this here. Ah, and I see it. It's right here. So it's important because this is the opposite, right? This is the reduction of the Pb2 plus to make Pb. And so I'm going to write this number down, but I am going to, forgotten it, I'm going to write this number down, and then because this is the opposite, this is an oxidation, I'm going to change the sign of this, make it positive. Okay? So whenever you have a reduction reaction, you just write the number from the list. And whenever you look at the oxidation part of your redox reaction, it's going to be the reverse, right? This is just the reduction on this particular list, but you're going to reverse this number to make it oxidation. Just switches the sign. Again, this would, when you're balancing the redox reaction, you're multiplying this by 2 because you want to have 2 electrons on the left, 2 on the right, but that doesn't change the voltage that you need. So the last step is adding the voltage. And so you have plus 0.13 minus 0.41. So what's the total voltage? The total voltage for the cell is minus 0. I believe that's 28 volts. So what does this tell us? Well, if I go back up here for a second, right? I added up the reduction potentials, and now if it's positive, then it's a spontaneous reaction. But in this case, it's negative. So this is going to be a non-spontaneous reaction. And what this means is that you're going to have to add at least 0.28 volts into the cell in order to make this reaction occur, probably a bit more due to friction. Let's do one more. We're going to do this one below. And we'll write out the chemical equation here. So we're going to do 2 here. I'm going to do 2 here just to balance it. And now I'm going to write out the reactions here. So 2Cl minus 1, this goes to 0. So this is going to be oxidized. And then the reduction will be fluorine F2 plus 2E yields 2F1 minus 1. So now I'm going to start with the reduction and try to find that first, because that's the number that's directly there. I'm going to look for F2. And there it is. F2, it's a top one. This is very highly, probable, has a lot of potential for happening, the most probability for happening because it's on the top. So 2.87. Okay? And this is volts and it's positive. Now, this is the oxidation now, so whatever we find, it's going to be in the reduction format, not the oxidation. So whatever voltage we have, we're going to switch the sign to be either positive or negative, whatever is the opposite. Oops. So we're going to take a look and try to find, again, try to find the chlorine here. Ah, there it is. So to reduce chlorine is really also very probable as well, but to do the opposite is not very probable, right? Taking chlorine and bonding it together and oxidizing it is something that it does not want to do. So when we're writing this, we're going to write we're going to write, instead of 1.36, right? Was that correct? Yes. We're going to write negative 1.36. And then we're going to add, again, add these up. And negative 1.36 plus 2.87 yields 1.51. That's volts. And what does this tell us? This is a spontaneous reaction. Okay, so it does not need a voltage for this reaction to occur. And this is how we solve for the cell potential. Obviously, with these, we can also ask, what is the cell potential? But also, we could ask for the, balanced redox reaction. And in this case, we would be able to do that. Just write out 2Cl1 minus plus F2. I'm not going to include the 2 electrons because they're on both sides. And then you have Cl2 plus 2F minus 1. So this would be also the balanced chemical equation. Hope that was helpful.